Well, hello everyone, my name is Mark Emilka and I work as a product sales specialist at Olympus. I would like to welcome you at today's online webinar, and I would like to kindly ask you to keep yourself muted during the presentation in order to hear me properly. And do not worry, there will always be a space for a question after the presentation. Thank you very much and enjoy it. So today I'm honored to demonstrate our new digital microscope, which was launched last year, 2019, and which carries the name DSX1000. This fully motorized system combines main advantage of optical microscope, which is indeed the high resolution, with the advantages of digital technology such as extended focal imaging or the possibility of direct image processing. This system is capable of magnification from 20 to 7,000 times with maximum resolution up to 1 micron, which provides us with the possibility to carry out both macro observation as well as the micro observation. But let's focus on the system itself. As you can see, the DSX consists of 4 main parts. The first one is this, which is motorized zoom head that is equipped with the high resolution digital camera DP74, which can deliver the frame rate of 60 frames per second as well as the 4K resolution. The second one is the microscope frame, which you can see over here, that is very massive and rigid in order to prevent unwanted vibrations of the system, and it's easily tiltable by 90 degrees in each direction, so it's possible to inspect your sample from the sides as well. You can see that another part of the motorized zoom head is also the objectives, which has a slide-in, slide-out mechanism, and Olympus offers a wide variety of them. At first, these are the super long working distance objectives. The second ones are the standard long working distance objectives. And these are the standard metallographic objectives UIS2. These are the diffusive adapters, and this is the polarizer for the long working distance objective. Next part is the motorized stage. You can see that it can be also rotated in 90 degrees in each direction. So basically we are able to observe our sample from any direction except of course its bottom. The last part of the DSX1000 is the console controller. And this really makes your life easier because you can carry out basic inspection almost without touching the keyboard or mouse. You can see it can be easily moved around the stage, zoomed in or out, or you can use one of these acquisition buttons as well. Okay, so let's leave the hardware behind and let me introduce the basic workflow with the DSX1000. At first, we of course place the sample on the stage. As you can see, the super long working distance objective is already mounted. You can see the outstanding working distance. And at this point, the only manual step follows, and that is the rough focusing with this focusing knob. There, we are in focus. At this point, you usually want to see an overview of your sample so that you can better orient yourself on it. For that, we will use the quick panorama function, so just click here and you can see that the stage starts to move in the XY direction, and it is collecting images along the way which are stitched together. You can see that even though the automatic exposure is not an easy task in this case, as we have very dark and very bright areas on the same sample, we are able to acquire and stitch this overview image. And then, if you go back into the live mode, the image is stored in the top right corner as a map image, and with this you will never get lost on your sample, not even while moving or using the optical zoom function. Now let's talk about one of the main points of digital microscopy, the extended focal imaging, or in short, EFI. We frequently observe that within one focal plane we cannot focus properly on every detail. Like for example here, where the bottom of the sample is in focus, but these connection pins are clearly out of focus. So what can we do? Well, with the DSX1000 it is easy. With one press of a button, the system scans through the Z-axis and takes images along the way, and these are stitched together into one fully focused image, the EFI image. Previously we have used the quick 3D mode, but sometimes it is more convenient to set the boundaries for Z scanning manually. For that we can use the start and end 3D acquisition. You find a region of interest, for example this resistor on the PCB, and simply move to the lowest position where you set the start position. And then you use the focusing knob on the console to move to the highest position, and you set this as an end position. Then you hit the start button and the system scans through the preset region and creates an EFI image. Now you can see the live acquisition process, and in a few seconds we will have a fully focused 3D image created with the preset boundaries. But it is not only about nice images. We can see that the acquired data as well are produced in 3D, and also we can perform measurements on these. For example, a very simple profile measurements where you select a cross-section plane like the one which you can see here and the features of interest, and measure then, for example, height or angle between these features. After you export your data, you can easily transfer them to CSV or to Excel, or you can use the reporting function within the DSX software, where you will find the predefined Olympus templates, which of course can be adjusted according to your needs. So you can get rid of some of the features, you can add some of them, you can enhance them. This is basically up to you. The next thing worth mentioning is the tilt possibility. Look at this region of interest, and let's say we would like to inspect if the chipset pins are properly connected to the board. As you can see, even using the optical zoom, we are not able to see the needed spot because we are looking directly from above and the pins are blocking our view. Usually not possible to solve, but with DSX1000 you simply tilt the microscope and then you can use the optical zoom function to see the previously hidden details. At this point you can even use the image processing feature, for example enhancing the depth of focus. Yes, you can see some of the areas which were previously out of focus become in focus with this. Or you can even acquire a 3D image while tilted to have a fully focused EFI image. As DSX offers large variety of illumination methods, it can happen that you simply don't know which one would be the best, or you just encounter a very difficult sample to illuminate. For that, there is the best image function within the DSX software. You simply hit the best image button and click all modes. And the system scans through all of the possible illumination methods and show you the preview image of them. Later, you can browse through these and decide which one suits you the best. Is it the bright field or dark field, or maybe the combination of these, the mix mode? Let's try the oblique mode, and you just double click on it and it is automatically set. Then you can just hit the autofocus, and like that we have the image ready, for example for the 2D acquisition. Nice and easy. Sometimes it is necessary to acquire the 3D profile from large areas. For that we can use the combination of stitching and 3D imaging, the so-called high-quality panorama mode. You have to start with the Z-axis. Again, you find the lowest focal position and set it as the start. Then you move to the highest position and set it as an end position. Now we have to deal with the XY stitching. So you enter the high-quality panorama mode, and in there you define the start position of acquisition as well as its end position, like that. Then you hit the start button, and system will take and scan the preset area, and on each spot it will create an EFI image. You can as well see in the bottom right corner that each Z range is approximately 2000 microns, and each 43 microns approximately an image will be taken, which gives us 45 images on each XY spot. You would say that this process will take a very long time, but see the speed of the process. We won't be waiting long for the final image. After this process is completed, there will be just a few seconds to stitch the acquired data together into an overall image. As you can see, we are now stitching 20 Z stack images together. And here it is. The final image is created, and we can see it in standard 3D, or as, for example, a wire model or a height map. But again, we are not doing this only for the nice images, but mostly for the precise measurement. At this point, we can go to, for example, the profile measurements again, but now inspect, for example, the cross-sectional area of the sample. You set the cross-sectional plane, and then you have to set the boundaries for the calculation. Okay, so we will set the left and right side boundaries, as well as the bottom one and the top one. The area is calculated right away, and you can export it very easily. Besides the profile, you can, for example, use the step measurement function to measure height differences between certain spots on the sample. We go into 2D, you press to define the measurement points directly on the image, select the multipoint function and input as a rectangle, from which the average value will be taken. Then you zoom into your image and define the points of interest. The first one, we have the second one, and for each point you export the data. Now you can see the height directly, define next point and export the data again. Let's do it a few times more to get the proper statistics. After you're satisfied with your data set, you can again easily transfer it into a report using the predefined templates. And again, these can be very easily adjusted to your requirements. So getting rid of some of these objects, enhancing some of these, or replacing, just create the report that is most suitable for you. So far, you may have noticed that we were only using the reflected illumination, which can lead to a question if DSX does support the transmitted illumination as well. The answer is yes, transmitted light is possible, and we can use it, for example, for samples similar to this one. You simply place it on the transmitted light adapter, then you have to, of course, turn the transmitted light on. Find your spot of interest and then adjust the focus roughly. And we can use again the high quality panorama, but this time only in 2D, and create a stitched image for a subsequent analysis of this inner hole. And why to use the transmitted light? Well, just look at the contrast of the final acquired picture. We have just the ideal conditions for semi-automatic measurements because we have a very bright region which is directly bordered with a very dark region. So you enter the measurement and then you enter a so-called caliper measurements. Then you have to select the outer and inner boundaries for automatic detection. So you can see now I'm setting the outer boundaries out of the boundary of the hole, and then the inner boundaries, so that the boundary we would like to detect is between these two circles. And now we have to play a little bit with the intensity histogram thresholding. At this point you have to think a little bit. What am I looking for? As we are going from outside, from the darker area, to the inside, the brighter region, we are looking for a start of the peak in the histogram, as the highest value represents white and the lowest is black. So let's switch to start peak, measurement type, and put a threshold value to the peak that represents the inner hole. While zoomed, you can see the red light indicating the automatic measurement. Yeah, this one. And again, you can then directly export the data of, for example, center, radius, area, or circularity of this object. One of the very new features which were implemented into the DSX1000 is the shadow contrast mode. You can easily access it from the best image function, where you hit the shadow contrast button and the sample will be scanned with an illumination going from different directions, which highly enhance the surface topography. Very good for fine surface details observation. Again, you double click on the best one, check if it's the best, and you can as well change the direction of light and take the image. We are still missing one of the very important possibilities, and that is the analysis of linear and surface roughness. For this procedure I have used the sandpaper as a sample. In order to acquire precise data, we have to switch to high magnification and high resolution objective, like the 40x one, and then use the optical zoom to get to the 1000 magnification, which provides that resolution of approximately 1 micron, which is, as it was said, the limit for this device. Then it is necessary to perform again the high quality panorama, so that we have a sufficient data set for both linear and area roughness analysis. So I have selected an area of 6 field of views in one row. Then again I had to set the start position for the z-axis. At this point we have to be careful because we are not doing this for only one field of view, but for the whole area. So now I'm browsing through the areas and checking if the bottom boundary is alright. Now going to the very highest focal position, which is over here, and now scanning back. And again checking if the highest position is okay for every field of view. You can see this one, it needs to be even higher. So I updated it. Okay, now everything seems to be alright. So I can press on and the 3D acquisition can start. After the analysis is done and the final image will be displayed, we can check it in the 3D view. If, for example, there aren't any errors or issues with it. And if we are satisfied, we can go directly into the measurements option and to the line roughness module. There we just go, let's say, step by step, starting with the possible inclination correction or noise correction. Then we, of course, select the profile line, the needed analysis parameters, and the cutoff frequencies if needed. After all of this is set, you can again easily export the data into datasheet and then further export into CSV or Excel. The procedure is more or less the same for the surface roughness. You start with the, again, surface correction, inclination and noise, and then decide if you would like to examine the whole image or just certain region of interest. So let's say I would like to examine only this region of interest. You set the needed output parameters and cutoff frequencies. And then you hit the calculation button. And again, the whole process ends up with exporting of these data into datasheet, and then of course CSV, Excel export or report creation. That is again up to you.